Hello, my name is Mustafa Siraj, roll number MEB18010, and this video is on the explanation of the questions given to us for Sessional Test 2 on the course of Fluid Mechanics 2 ME209. So in the first question, we have been given a prototype hydraulic turbine which operates at a speed of 95 revolutions per minute at a head of 15.24 feet and produces an output power of 26.845 megawatt. The laboratory facilities are available to make a model hydraulic turbine which operates at a head of 4.572 feet, produces an output power of 37.285 kilowatt and runs at an hydraulic efficiency of 86% or 0.86. Now we have been asked to find out A, the model test speed and scale ratio, and B, the volume flow rate. So I have taken all the values of prototype hydraulic turbine with subscript P, and I have denoted all the values of model hydraulic turbine with subscript M. Now we'll start with A. To find out the model test speed, I have used the concept of unit speed, which is the speed for 1 meter head and which is constant for both prototype and model. So it gives us Np divided by root over Hp is equal to Nm divided by root over Hm. By rearranging, we get Nm to be equal to root over Hm by Hp into Np. By putting in the suitable values, we get Nm equal to 52.03 revolutions per minute. Now to find out scale ratio, I have used the head coefficient of Buckingham's pi theorem, which states that root over Hp by dP Np is equal to root over Hm by dm Nm. Here dP and dm are the diameter of the wheel of the turbine of prototype and model. By rearranging this, we get dm by dP is equal to root over Hm by Hp into Np by Nm. As we know all the values, we'll put the suitable values, and we got dm by dP to be nearly equal to 1, which is the scale ratio. Now part B, to find out volume flow rate. I've used the concept of hydraulic efficiency, which is given by eta h equal to Pm by rho Q G Hm. Here Q is the volume flow rate. By rearranging, we get Q to be equal to Pm divided by eta h into rho Ghm. Putting in the suitable values, we got volume flow rate Q to be equal to 3.173 meter cube per second. Now we'll come to question 2. In question 2, we have been given a Pelton wheel, and the inlet conditions of the nozzle are given to be pressure P1 48.2633 bar, velocity V1 to be equal to 24.14 km per hour, which when converted to meter per second is 6.17 meter per second. Nozzle loss coefficient K to be equal to 0.04 and hydraulic efficiency eta h to be equal to 86% or 0.86. Here I have made this diagram of the nozzle. The inlet conditions are V1 and P1 and outlet conditions are V2. Here pressure is almost equal to atmospheric pressure, and the diameter of the outlet is given in question to be 19 centimeter or 0.19 meter. The diameter of the wheel is given to be 2.44 meter, and I have taken the velocity of the wheel to be u. Now in the question, we have been asked to find out A, the power output, B, the normal operating speed, C, the approximate runaway speed, D, torque at normal operating speed, E, torque at zero speed. So we'll start with A. We know that power output of a Pelton wheel is given by rho Q G H eta h. Here we know all the values, but we don't know Q and H. So we'll have to find out Q and H. Let us mark this equation as equation 1 and try to find out Q and H. So we'll start with Q. As we know that Q is the volume flow rate, and it is given by A2 V2, where A2 is pi by 4 small d square. Small d, as we know in the question, is given to be 0.19 meter, so we'll put it, but we don't know v2, so we'll have to find out v2. Let us mark this equation as equation 2 and try to find out v2 by the help of Bernoulli's equation at the inlet and outlet conditions of the nozzle, which gives us P1 by rho g plus V1 square by 2g is equal to V2 square by 2g plus k V2 square by 2g. Here, as I said earlier, that at the outlet pressure is equal to atmospheric pressure, so pressure head is not taken, and the k V2 square by 2g, this term constitutes for the change in kinetic energy. By rearranging this Bernoulli equation, we will be able to find out V2, which is equal to root over 2 divided by 1 plus k into whole of P1 by rho plus V1 square by 2. We know all these values and we got V2 to be equal to 96.45 meter per second. Now putting this V2 in equation 2, we can get Q to be equal to 2.73 meter cube per second. Now we'll have to find out H. As we know H is the net head, which is given by P1 by rho g plus V1 square by 2g. We could easily get H to be equal to 494.76 meter. Now as we have got both Q and H, we'll put them in equation 1 and output power is obtained to be 11.39 megawatt. Let us come to question number 2. Sorry, part B of the question number 2, where we have been asked to find out normal operating speed. Normal operating speed is the speed at the maximum efficiency. So we'll take the help of this graph at the right hand side, which is between efficiency of wheel and ratio U by V2. We can see here that ideally efficiency of wheel is maximum when the ratio U by V2 is nearly equal to 0.5. But in real conditions, efficiency is also reduced and the ratio U by V2 is also reduced to some extent. U by V2 is nearly equal to 0.46 for maximum efficiency, so we'll take U by V2 to be equal to 0.46. As we have earlier obtained V2, we'll be able to find out U by putting the value of V2 96.45. we got U to be equal to 44.36 meter per second. Now since we know that U is equal to pi and d by 60, we'll be able to find out the normal operating speed Nn to be equal to 60 U by pi d, where U is the 44.36 as we obtained earlier. So N subscript N is equal to 347.39 revolutions per minute. Now we are asked to, in part C, we have been asked to find out the approximate runaway speed. This is the speed at the maximum unsafe, this is the maximum unsafe speed of the Pelton turbine. So again we'll come to this graph and see that when is the maximum unsafe speed obtained. When efficiency is minimum, of course, and efficiency is minimum at 2 points, when the ratio U by V2 is 0 and when U by V2 is equal to 1. If U by V2 is 0, then there will be no flow, so of course U by V2 have to be 1 for the speed to be maximum unsafe. So it implies that U will be nearly equal to V2 and equal to 96.45 meter per second. So again, using the formula U is equal to pi and d by 60, we will be able to find out maximum runaway speed N subscript R, where U will be 96.45 and maximum runaway speed NR will be equal to 755.32 revolutions per minute. Now in part D, we have been asked to find out torque at normal operating speed. We know that ideal torque is given by the formula rho QR into V2 minus U into 1 minus cos theta, but torque at normal operating speed T is somewhat reduced according to its efficiency, and it will be equal to eta into T ideal. So its formula will be T equal to eta rho QR into V2 minus U into 1 minus cos theta. Here we know all the values, and theta is the angle of deflection, the angle by which the fluid flow deflects after hitting the wheel of the turbine, which is specified to be 165 degree for maximum efficiency. So we'll easily be able to find out T to be equal to 292.851 into 10 to the power 3 Newton meter. Now in part E, we have been asked to find out torque at zero speed, that is u0. So again, using the formula T is equal to eta rho qr into v2 minus u into 1 minus cos theta, and putting the same values again, only the change is here when is that u is 0. We will get torque T to be equal to 542.245 into 10 to the power 3 Newton meter. In question number 3, we have been given a reaction turbine of Francis type whose outer diameter is 4.5 meter and it produces a power of 54 megawatt. It operates at a speed of 107 revolutions per minute at an efficiency of 93% under a net head of 65 meter. Length of the penstock is given to be 400 meter and net head is given to be 83% of gross head. Now we have been asked to find out A, specific speed, B, volume flow rate, and C, the penstock size. So we'll start with A. Specific speed of Francis turbine is denoted by NST, and that is equal to NP to the power half H to the power 5 by 4. As we know all these values, we will be easily able to find out specific speed NST to be equal to 134.72. Now in part B, we have to find out volume flow rate. So we will use hydraulic efficiency again here. Eta is equal to P by rho Q GH. So Q will be equal to P by rho GH eta. As we know all this value, we will be able to find out volume flow rate Q to be equal to 90.28 meter cube per second. Now in C, we have to find out penstock size. We'll know that by definition of head loss, HLT will be equal to acceleration due to gravity into frictional head loss, and that is equal to F into L by D into V bar square by 2, where F is frictional factor, L is length of penstock, D is diameter of penstock, and V bar is the average velocity. So let us mark this equation as equation 1 and try to find out all the values that we don't know here. So as we have been given in this question we have been asked in this question to find the penstock size. That means the diameter of the penstock, this D is to be found out. So we'll try to find out rest of the values and then we'll be easily able to find out D. So we know that gross head is equal to net head plus frictional head. That implies that frictional head is equal to gross head minus net head. As this is given in question that net head is 83% of gross head, this leaves us with 0.17 of 17% of gross head or 0.17 of gross head. So frictional factor will be equal to 0.17 into gross head, as we know is net head divided by 0.83, and net head is given to be 65 meter. Frictional head will be equal to 13.31 meter. So we got HF of this equation 1. Now we'll try to find out average velocity V bar, that is equal to Q by A. Now we know that A is equal to pi by 4 into capital D square. Capital D here is the diameter of the penstock. So squaring both these terms, we will get V square to be equal to 16Q square divided by pi square D to the power 4. Now we'll put this V square in equation 1 and get GHF to be equal to F into L by D into 8Q square divided by pi square into D to the power 4. Rearranging it, we will get D, diameter of the penstock, to be equal to 8 into FLQ square divided by pi square into GHF to the power 1 by 5. Now we know all the values, but we don't know F here, so we'll have to find out F. We know that in the Moody's chart there are 3 axes. One is of a frictional factor, one is of Reynolds number, and one is of surface roughness. So to find out F, we'll need to know surface roughness and Reynolds number. Let us assume the penstock to be concrete lined, which gives us the epsilon permittivity to be equal to 0.003 meter. So surface roughness could be found out as epsilon by D naught, as we know that epsilon is for concrete line 0.003 and D naught in the question to be 4.5. we will get epsilon by D naught to be equal to 0.0006. Now Reynolds number is equal to rho V D naught by mu. and we know that this V is equal to 4Q by pi d square. So we'll get Reynolds number to be equal to 4 rho Q divided by pi mu d naught. As we know all these values, we'll able to find out Reynolds number to be equal to 2.55 into 10 to the power 7. As we now know both the surface roughness and Reynolds number, we'll be able to find out frictional factor from Moody's chart, that is equal to 0.017. Now we'll put this F in equation 3 and find out diameter of the penstock to be 3.21 meter. In question number 4, we have been given a propeller turbine which produces an output power of 22,000 kilowatt, operates under a head of 20 meter and speed 150 revolutions per minute. Hydraulic efficiency is given to be 95%, overall efficiency 88%. The diameter at the outer periphery is given to be 4.5 meter and diameter at the hub is 2 meter. We have been asked to find out runner vane angle at hub and outer periphery. So I have first drawn the velocity triangle at the inlet and the outlet. The velocity of the rotor is the velocity of the runner I have taken to be u, and the absolute inlet velocity is v1. Its whirl component is vw1 and flow component is vf1. Its relative velocity to the runner is vr1, and velocity of the runner as seen from the inlet is u1. Here runner vane angle is beta1. As given in question, the whirl component of velocity at outlet is 0, so the absolute velocity at outlet will be equal to the flow component of velocity only, and axial in direction. So v2 will be equal to vf2 here. vr2 is the relative velocity of the outlet, and u2 is the velocity of the runner as seen from the outlet. Here beta 2 is the runner vane angle at the outlet. So in the question we have been asked to find out this beta 1 and beta 2. To find out beta 1 and beta 2 from these triangles, we will have to find out the velocity components. So first we'll try to find out the whirl component of velocity at the inlet. So we know that hydraulic efficiency eta h is equal to whirl component of velocity at the inlet multiplied by velocity of the runner as seen from the inlet, u1, divided by gh. So by rearranging we get vw1 to be equal to eta h into gh divided by u1. Now we know that u1 will be equal to pi d naught n divided by 60. So we'll put the suitable values and get 5.26, vw1 to be equal to 5.26 meter per second. In propeller turbines we know that flow component at inlet is equal to flow component at outlet, so we'll mark this as 1. Now we'll see the velocity triangle, the velocity triangle at the outlet, and see that tan of beta 2 will be equal to vf2 divided by u2. So we'll have to find out vf2 and u2. We know that overall efficiency will be equal to power developed at shaft divided by power supplied at inlet. So power supplied at inlet will be equal to power developed at shaft divided by overall efficiency. That will be equal to 22,000 kilowatt divided by 0.86, and that is equal to 25,000. So we also know that power supplied is given by the formula rho q gh, and that is in watt. So to convert it in kilowatt we have divided it with 1000, and that is equal to 25,000 as we have found it earlier. So from this we'll rearrange and get q to be equal to 127.55 meter cube per second. Now we know that q for a propeller turbine could be found out by the formula pi by 4 d naught square minus d h square into vf1. Putting in all the values, we'll able to find out Vf1 to be equal to 9.99 meter per second. Now from 1 we know that Vf2 is equal to Vf1 and that will be equal to 9.99 meter per second. Now we know that U2 is equal to pi dh n by 60. Here dh is 2 meter, so that will be 15.7 meter. Now equation 2 could be written as tan of beta 2 into Vf2 by U2. Vf2 and U2 we have found it out, 9.99 meter per second and 15.7 meter per second respectively. So tan of beta 2 will be equal to 0.63 and beta 2 will be tan inverse of 0.63, that will be 32.21 degree. And this is the runner vane angle at the outlet. Now we'll again see this velocity diagram at the inlet, where tan of beta 1 will be equal to Vw1 will be equal to Vf1 will be equal to Vf1 divided by Vw1 minus U1, which I have written in equation 3. In equation 3 we have been able to find out Vf1, Vw1 and U1 to be equal to 35.34 meter per second by the formula pi d naught n by 60. So tan of beta 1 will be equal to minus 0.33. So beta 1 will be tan inverse of minus 0.33 and beta 1 will be 161.8 degree. That is runner vane angle at the inlet. So we can see that runner vane angle at the inlet is an obtuse angle and runner vane angle at the outlet is an acute angle. We can see this in this diagram also, that beta 1 is an obtuse and beta 2 is an acute angle. So we can verify that these angles we have found are correct. So that's all for my explanation. Thank you.